brief history of cellular because it is kind of interesting when you look back, and a lot of people are surprised by this. My goal with all of this is I'm going to give you some talking points. So you can go home and your spouses, significant others, kids say, what were you doing in Austin? And instead of saying property tax, you can say, well, did you know, right? We'll talk about architecture deployments. I'm going to talk about the 5G networks, how they've deployed. Some of that stuff I've covered before. We are going to talk about 5G Advanced and 6G. I'm going to talk about spectrum and the prospects for more of it, because we do need more. Jurgo is nodding his head like, yes, please give me more. And we're going to have to talk about AI, of course, right? So number one, history. 1946, the Bell system was launched for cellular. And actually, it supported cars. It was launched in St. Louis. And in the entire city, you could have 3 calls. Right? And literally what you did was you picked up this handset in your car, and there was an operator at the end, and you said, I want to talk to Bill. And she's like, okay. And she would put you through to Bill. That's literally how it worked. By the end of 46, it actually got up to 25 cities, but it was all manual. The first automatic system came in 48, and that's when you can actually pick it up and actually dial a number, and it would connect you through. So this stuff ain't new, right? We went on. The first cell phone call is claimed by Motorola, Marty Cooper, in 73. I know Marty pretty well. I don't think he's on the call. He's not on the call, is he? No. He's been kind of cashing in on that since 1973. I've also met the people from Ericsson who said, no, we beat them by a week. And then somebody from Siemens in Germany said, actually, we beat the Swedes by a week. So there's like 3 people in the world I've met who claimed the first phone call. But the one that is on the books is for Motorola and Marty Cooper. First commercial network was actually in Saudi Arabia in 81. Ours was 83. And I find this really interesting. If you are 43 years old or younger, you've never lived in a world without a cell phone. If you're 18 or younger, you've never lived in a world without an iPhone, which is kind of, for us old folk, it's kind of scary. Nokia, new first phone in 87. My dad had a 1980 Volkswagen Jetta GLI. It had Nokian, Nokian tires on it. So Nokia did make tires and diversified into cell phones because, as you do. 3G was in 2001. BlackBerry was launched in 2002. If you haven't seen the BlackBerry movie, and I can't remember what it's called, it is quite excellent. For a lot of people in the room, it'll be kind of scary because we probably know Jim Basile and all those guys. I was in some of those meetings that are in the movie, and it is hilarious, and it's all true. It was that crazy. iPhone, and then 4G was actually 2009, which that's 15 years ago. 5G was 2019. So it's A, not new, and B, we've gone through a lot of Gs. And I've said this before, we need to get rid of the Gs. My dad is 82. We keep having the same discussion about his 5 gigahertz Wi-Fi is 5G. I'm like, no, 5G is the cell phone. My dad's a bit of a techie guy, but gets 5 gigahertz and then 5G. And yes, we have new spectrum for Wi-Fi, and guess what band it is? Anybody know? 6 gigahertz, 6G. We're already doing it to ourselves. So we are our own worst enemy. Bandwidth keeps going up. So this is the main, obviously the driver. This looks like a straight line. It's actually not. It's got a curve to it. But typically, the rule is 40% every 2 years or something. And we keep thinking, oh, in the next 5 years, it's going to level off. No, it keeps going up. This is the total mobile data traffic in terabytes per month. This is the amount of traffic on a per user basis. And people look at this and go, yeah, 2024, 25 gigs. Nobody's using 25 gigs. Yeah, they are. Go look at your bill. Go look at my son. And this is actually my son's new TV. He got a new apartment with his girlfriend in San Francisco last summer. And the first thing Jordan did was buy an 84-inch TV. If you look at it, you see that elbow sticking out there on the left? That's his girlfriend's elbow. She's like 5'5", and she comes like halfway up the image. This thing is huge, right? And I said to him, well, how are you connecting to the web? I don't know. Well, what are you doing right now? You just moved in. Well, I'm doing it on my cell phone. So he's just tethered his cell phone to the TV, just streaming stuff. Yeah, a couple of days, 10, 20 gig. Yeah, till he got Comcast set up. Don't worry about it. Yeah, go somewhere. I travel. I don't typically use Wi-Fi in hotels. I'll use 5G. And I was in the UK last week. I can easily go through 10 gig, stream a few Netflix shows and a bit of BritBox, and you can easily do it. Movies are all HD, right? They're big files. So this going up 2028, 50 gig a month per user. That means a lot of people will be using 100 gig. Does that sound crazy? Yes. Is it when you've got 4K TVs and stuff and images? And look at the new iPhones. This is a 15. The quality of the images on here, the density of pixels. You start sending photos around and video. Video is the killer. A lot of this is driven by video. And we will talk about AI, but the power of AI is not ChatGPT, right? It is not, can you write me an email telling my boss he's an idiot, but make it sound good, right? That's easy stuff. The power of AI is, here's a video I shot. Can you please insert Taylor Swift into the background so it looks like she's talking to me, right? I'll upload the video, process it, and bring it back down. That is a lot of bandwidth and a lot of processing power, and that's what people are starting to do, and that's what will drive a lot of these numbers. We'll come back to this because this has got huge implications. For all of these megabytes and gigabytes, we've got to have a network support it, right? Ruben talked about the data center processing at the other end. He mentioned the fiber connecting the data center to the internet. He didn't mention all the towers and radios needed to connect to the end user, because in my son's world, it's all wireless. Whether it's Wi-Fi or cellular, it's all wireless. So, all right, I said we're going to break it up. Long story short, there is a really cool smart telescope out there called the C-Star S50. And I've got one on order. It's about this big. Turns out a friend of mine had one, and I wanted to try it, so I borrowed it and bought. It is amazing. It is, take a telescope, strip out all the stuff you don't need, like an eyepiece, put in a really good sensor and some optics and a lot of very smart electronics, GPS, and the software is all built in. And it takes amazing photos. And it's $500. So for people like me who have a big telescope and set up cameras and like are trying to find, Jupiter, and then Jupiter moves, of course, so you have to keep moving it. It is a godsend. It's brilliant. So I borrowed it and took this. This is the Orion Nebula. You can actually see the Orion Nebula with your naked eye if you just look up. If you look at the belt of Orion, those 3 stars in a row, it's down the southern end of there, and it looks like a fuzzy star. Because it's not a star, it's a nebula. It's a bunch of gas and dust. And the bright bits in the middle there is actually where stars are born. So a star is basically a bunch of gas and dust and things that coalesces and then reaches critical mass and then basically bursts into flames, and bingo, you got a star. So this is where stars are born. The whole nebula is about 2,000 times the mass of our sun, okay? But here's the kicker. It's 1,344 plus or minus 20 light years from Earth, okay? So that picture was taken over the holiday on the sea star. So that light left the Orion Nebula back in the early Middle Ages. Now, I actually went to look about who was King of England at the time. There was no US at that time, in case anybody's wondering, right? And it's nobody you'll know. There was no Great Britain, no United Kingdom. It was all a bunch of tribes beating the crap out of each other. It's basically the English beating the Scots, right? All those guys with the blue faces. I was one of the guys lobbing arrows, if you watch Braveheart. So anyway, so that's it's pretty cool. You can actually say, you can look up and see it. To get this type of image, you've either got to buy a cool telescope or go on the internet. But it's pretty slick. And everybody wants to, I can tell you more about how this telescope works. It's quite clever. All right, back to networks. See, I told you I was going to mix this up, make you pay attention. So physical network, I've used this before. I thought I'd just run through it. You've got the radio access network. This is the radio, the antennas obviously talks to the device. We've got a spectrum, we have different spectrum bands. Each band propagates differently. So the lower the frequency, the further it goes, right? And the reason there's difference is when it goes through the air, in the air there are water molecules. When the radio wave hits a water molecule, it disperses. Radio waves do travel differently in Seattle and Texas, because Seattle has more water in the air because it rains more. And there's plenty of stories, and they're true, of like Boston, you know, they set up a network in the summer, there's leaves on the trees, everything's great, and it snows in the winter, and the network performance goes down because they tune the network for the summer, not with all the snow on trees and things like this. So, you need a radio and an antenna to transmit and receive. None of this works without spectrum. And spectrum is hard to get. We'll talk about this. But all the low stuff, we have 700 megahertz. The original cellular frequencies were 850. Then we had PCS at 1900 megahertz. Nextel was 2.5 gigahertz, 2500 megahertz. That's what Timo got. AWS, there's been different bands, AWS 1, 2, and 3. So I'm looking at Gary because he's got a bunch of AWS. He sits on about 2.1 gig, 2.2. There's the 2.3 gigahertz WCS band, etc. The newer stuff is all at 3 gigahertz, 3,000 megahertz. We talked about the new Wi-Fi, 6 gigahertz, 6,000 meg. As we go up, the amount of distance those signals can go through the air shrinks, which means you need more cells. So at 2.5 gigahertz, you need 3.7 times the cells as 700 megahertz to cover the same area. You go up to the 3 gig band, up to 4, 5, etc. You need a lot more cells. For 6G, we are talking about the 7 gigahertz band, as well as more 3 gigahertz band. We're going to need a lot more cells, right? That's a lot more radios, a lot more towers, a lot more stuff, a lot more equipment. So that's why it matters. Basically, it's pretty simple. You got an antenna, you got radios, it goes down to a baseband unit, a cell site router, and into the core network. The core is the bit that actually tells when I hit, yes, I want to call Ruben. It's the core that goes, Ruben, he's at 512, boom, 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 and connects the call through. Also, if I'm moving from cell site to cell site, I'm driving, it's the core that manages that movement, does the cell handoff, etc. This is what we basically had for 4G. This architecture didn't really change from the original analog cellular days in the early 80s to 4G. It was pretty much this. Our performance got better of the antennas. The radios used to be at the bottom. We had a big fat coax went up the tower, but it was heavy, expensive, and it lost power. So we moved the radios up to the top near the antenna. A radio is about the size of 3 pizza boxes stacked on top of each other, roughly. But we have to have the same radio as the baseband from the same manufacturer. They talk the same language. So Ericsson radio, Ericsson baseband, Nokia, Siemens, sorry, not Siemens, Samsung, etc. Okay. Now, what we've done, and this is pretty much what you see with the 5G deployment. Still got radios and antennas at the top, but at the bottom, we've got a DU and a CU. One of the things we like to do in the wireless world is change acronyms, because then we have to explain it all again. We sound smart, right? So we like the same box with a new acronym. That is just the perfect situation. So the radios are called the RU. See? Used to be radio, now it's an RU. DU is distributed unit. CU is centralized unit. What we did is we took that box there, the baseband, and split it in half. And we said we can put some of it at the tower and some of it in a local data center. So back to Ruben's presentation earlier this morning, and he was saying there's different types of data centers, and there's the cloud ones, and he talked about some of the local ones. Those local ones are where some of the CUs sit. They may be owned by a carrier, they may be leased, it may be in the basement of a building. It could be an old central office that has been repurposed. And then the core sits up in the cloud. This core in the cloud doesn't have to be in a carrier-owned data center. So Dish was one of the first to do this. They partnered with AWS, and they ran their entire core up on AWS infrastructure in their cloud. AT&T's done a deal with Microsoft Azure, same thing. Verizon is AWS, I think? Google? Can't remember. And I'm looking at Yurgo like he can tell me who T-Mobile is, and I can't remember either. You can't. You're just looking smart like, yeah. Two big data centers. They're pink. Sorry, it's magenta. And there is no correlation to the color here being blue, for that is not an AT&T data core. Right? I just like the color blue from PowerPoint. So this is pretty much how 5G has been built. Pretty flexible. We can move this stuff around at the bottom. Then you've heard of Open RAN, pretty much the same thing, except my radios are different colors from my DU. Now I can mix and match my vendors. Okay, so I can have a Samsung radio with a Ericsson distributed unit. I can have a Samsung and Mavenir and Ericsson radio all on the same tower talking to an Ericsson or Nokia distributed unit. Gives me more flexibility. Very much so, all this is software based as well. You can do upgrades. This is important because when we get into 5G advanced, the new standards, do not assume we're going to rip all these radios and baseband units out and put in new stuff. No, a lot of it is a new software load, a new firmware update. It's software based. Depends on the age of the radio. They do age out. They get to a point just like your phone where you can't go to the newest version of software, right? But a lot of this is designed for 3 and 4 type releases of software. So for all you property tax people go, oh, great, they're going to rip out all that equipment and put up new stuff and I can build them more. Not necessarily. And again, a lot of it is going into the data center, which may not be owned by the carrier in the first place. And final thing, these servers down here are off the shelf. Ruben on his presentation had Dell, you mentioned Supermicro, etc. These are standard computing servers, off the shelf, put them in the rack, off you go. Will we see GPUs down here? Not yet. Talking about it. But what Ruben didn't mention, he kind of hinted at this on one of his charts. Those little NVIDIA GPUs are like 15 to 20 grand a piece. Whereas a regular server is, you can get a server for $1,000 these days. They're expensive. What we are talking about, Ericsson's discussed this, is putting a GPU in the back of the radio. So your request comes from your phone to do something AI-y. it goes straight to the radio and gets processed and sent straight back. Doesn't even hit the rest of the network. Obviously, it's going to depend what the request is, but that type of power is what they're talking about. That means the radio is going to go from being a couple of $1,000 up to $30,000 or more. And then you've got a power issue. There's a lot of issues. So this is not happening next year. This is way out there. Okay? Make sense? Clear as mud? Still awake? 5G is not really about deployment anymore. It's about monetization. Having said that, the carriers have deployed about half of the spectrum they have allocated for 5G. We're not done yet with the build. We've got more to go, which is good because we need to get more out of it. But it really depends. 5G got kind of a bad rap. I think a lot of this was due to COVID, because just as we were starting the rollout, COVID hit and everybody ran home and got on their Wi-Fi and worked from home, etc. The build out was kind of, I won't say stalled, but it was certainly hindered. But depending on who you talk to, 5G is either undelivered and not lived up to the hype, or yet to deliver on its true promise. I tend to be in the second one there. We are getting more deployments, more coverage, more capacity. But we're really talking about how we recoup the investment here as an industry. What services and apps can we put on? Fixed wireless access for the home is the big one that is, the last couple of years has captured a lot of the attention. But then you talk about self-driving cars and stuff like that. No. Next thing is a lot of private networks of gaining ground here. Network slicing is when I take a chunk of the network and dedicate it to a specific application. Those types of things are coming on stream now. Private networks had a pretty good year last year. But really, that's what we're talking about, is 5G monetization. How do I make money out of it? So what's coming next is 2000. I said 5G was 2019. The standard was actually approved in 2018. It was 5G release 15 non-standalone. What that means is we had 5G radios with an old 4G core, right? Which is the same as taking a nice shiny Mercedes, and it's all outside, it's all flashy and great, and under the hood is a 30-year-old engine that's complete, I won't say a complete dog, but it was a generation, right? The first real 5G was release 16, which was approved in 2020 and started deploying late 21. The reason there's this gap is once the standard is approved, it takes Ericsson, Nokia, Samsung, and co. a year, 18 months to actually build the equipment, design it. And what release 16 gave us was standalone. So we had a 5G core with the 5G radio. Originally, release 16 was going to be 5G. But some of the folks pushed for release 15 from a marketing point of view. And that's why we got this kind of divided 5G radio, old core, then 5G radio with new core. The URL LLC is ultra low latency. Low latency. That's the fast response from the network. That came with release 16. Release 17 gave us more of the same. And then last year, release 18 was approved. It'll go in the market early 26, mid 26, you'll start to see it. That is 5G advanced, it's called. And basically, it's more 5G, but it's focused around AI and machine learning for the operation of the network to make it more efficient. And it's also tailored towards augmented reality and virtual reality, which I know you're all really excited about because you've all rushed out and bought your Meta headsets and your Apple Vision things for $3,000, and you're just sitting there waiting for 5G to deliver this for you. And finally, somewhere around the middle of 2026, you'll be able to use it. Yeah, we're a bit behind on that one. And AI here doesn't mean you're going to be able to use ChatGPT faster, right? It means that there are AI tools built into the network to make it more efficient, more power efficient, et cetera, et cetera. 5G advanced is going to give you higher speeds and few other things. Other than that, you're not really going to notice as the consumer. It's going to be a tough one. Doesn't stop mean that we won't market it. Release 19 is actually going to be approved later this year. We'll see it somewhere around 27. It's got support for massive MIMO. That's the big antennas with little big antennas. There's more support for those in there. This stuff, a lot of people argue this stuff should have been done back here. And they're not wrong. The original concept for 5G, all the things were promised originally, are actually what's coming in 5G advanced. So it's taken a while. Release 20 comes in 2027. Release somewhere commercially around, and that's just more of the same. And the big one is release 21, which is 6G. And you'll notice it says collaboration there, collab, and absolutely nothing else. So what is 6G? Anybody know? Good, because I don't. They're not even going to finalize the standard until 2029. That's 4 years from today, right? People are working on it. There's groups all over the world talking about it. But in actual fact of actually getting it finalized and what we will see in it, to be determined. When does it get deployed? You'll see trials in 2030 and maybe some trials in 2029, but really 2030 and beyond is deployment. So what this means is we're slap bang here at the beginning of 25. We've got 5 years to go with 5G, right? And Ruben's building all these data centers all over the place. And you know, we've got fiber companies. Who bought Frontier? Verizon did, right? You know, fiber going all over the place. The end access point, the radio connection from, you know, that to you is something that was actually developed back in 2020 and has been tweaked and tweaked and tweaked. 5G Advanced is not a new standard. It is not a new interface. It's just an upgrade to what we have, okay? So we've got a lot of work to carry. That bandwidth growth has got to depend on, it's got to carry that traffic for 5 more years, right? Originally, we thought 6G would be in earlier. It's not. And typically, 4G to 5G was 10 years. So this is another 10 years. There were some people hoping it would come sooner. It's not going to. So this is kind of important because, as I said, that bandwidth growth, we've got a lot of stuff we've got to do. And yes, along the way, will a release 20 radio be different from a release 17? Probably. We'll put new radios. But this stuff, release 21, what I didn't tell you is it's a 6G radio with the 5G core, which is what we did back in release 15. We had a 5G radio with a 4G core. So we're doing the same thing again. So yeah, any of you still around in 2030? Happy to discuss this. All right, stars. Now this one doesn't work out very well because it's a bit bright in here, but this is the Horsehead Nebula, and you're like, where the heck's the Horsehead Nebula? Just south of Orion's Sword. I don't know if you can see, if you turn out the lights here, there's a dark area there. If you go look it up on the web, you see it actually looks like a horse's head looking up and to the left. And again, it's, there you go, thank you. You see it there, look, and it's right there as well. You can't see this with the naked eye. You need a telescope to see this one. It's also called Barnard 33. There's all these different classifications. This one's kind of fun. It is just south of Orion's belt, as I said. Sorry, the belt, not the star. But it's 1,375 light years away, okay? But it was actually discovered by a Scottish lady called Wilhelmina Fleming in 1888. And she was actually a single mother from Scotland. She married her first husband. They emigrated to the States, to Massachusetts, Boston. And she was actually, there was a dinner party, And these people there from Harvard, Harvard has its own observatory and had all these plates, as they called them, which are basically photographic plates. They'd taken of different stars and nebulas, and they were looking for somebody to actually catalog them. And the host of the dinner party recommended Wilhelmina. She was actually their nanny who taught their kids, and but had a very, very analytical and organized mind. And so she went through these plates and realized that there was this nebula was there. Along about another 300 she discovered as well, just by looking at all these pictures. Go, hang on, what's this? And so she gets credited with it. Several things are named Fleming in Harvard. They're actually after her and a guy whose last name was Fleming, not related whatsoever. But yeah, the Scots. See, we Brits, I tell you, we're all over the place. You just don't realize it. I mean, Yurgo, that's not, no, not English. Let's not go there. Let's not go there. All right, so I mentioned spectrum. Here's the problem. There's no easy spectrum bands left, right? The 3 gigahertz band we used for CBRS, and then the 3 gig, the 3.45, that was relatively easy. We moved a bit of stuff around and there it was. 2.5 gig has been around for a while. AWS 1, 2, and 3 were slices we could access, and they're relatively small. The problem with what we need now is we need big chunks of spectrum for 5G advanced and 6G. The reason we get better performance on these networks is because we have bigger chunks of spectrum, and we can spread the load, if you like, across a bigger chunk of spectrum. So LTE, a full channel of LTE was 20 megahertz, right? It worked very well in 10 megahertz. 5G, a full band, is 100 meg, okay? Harder to find. 6G, they're talking about 5 to 800 megahertz, one channel. That's how much we need. Well, finding that is a bit of a problem. So the FCC, the NTIA have been working on this. The good news is that spectrum does exist. The bad news is the Department of Defense controls it, and they don't like to give stuff up. And they have meetings together where they go, you know, we'd like to talk about this band. The Department of Defense says yes. They have a meeting and say, what are you using it for? It's like, I'm sorry, I can't tell you, you don't have security clearance. So you go and find somebody with security clearance to come back and say, what are you using it for? They say, tanks. You say, what are you doing with the tanks? I'm sorry, you can't tell you, that's security, we need a higher clearance. And this is what happened with CBRS and the 3 gigahertz band. And the same thing will happen again. So whatever we do, we're going to have to involve the Department of Defense, right? I actually sit on the FCC Technical Advisory Council, and there's a working group on there called Advanced Spectrum Sharing, which I'm part of. It is to work out the mechanisms to work out how this is going to happen. And we're due to report in September. New administration just came in, you may have heard. We don't have a chairman anymore, things may change. So stay tuned on that one. But that's a lot of the challenge here, is finding that spectrum. Now, we can't, there's nothing easy left. We're going to have to share, right? The Department of Defense, probably the Navy, is going to have to share what they're using, and they don't like that. Best case, 2030 is when the carriers will get spectrum. Now you say, well, that's 5 years here. Can't we do something in 5 years? The FCC actually does not have spectrum authority at the moment to auction spectrum. Congress let it lapse a few years ago. It was in a reconciliation bill. They've been trying last year to get it back. They say it's going to happen this year. They've said that for the last 2 years, I think. So even if the FCC had some spectrum, they couldn't sell it because they're not allowed to by Congress. So that's the first problem we've got to fix. So if you look at the timeline, we're here in 25. Let's assume the FCC gets spectrum authority in 25, right? We then do our work and report back and tell you how we're going to do this sharing. And then the FCC is going to take a year to get comments back from the industry on the sharing mechanism and work it all out, how it's actually going to work. So that's the end of 25. That's the end of 26. Okay. Then we agree we're going to have some auctions and the band that's going to do, and then the structure of those auctions and how big the bands are and the licenses. That's another 18-month to 2-year fight. So now at the end of 28, then we have the auction. That'll take a year to 18 months. So let's call it the end of 29. And then we give you the licenses you've just spent billions of dollars for, 2030. That's how fast things go. It's a big deal. It's a lot of complication. There's a lot of moving parts. Could it be later than this? Yes. Not to pick on two people sitting in the room, but I did share a cab with somebody from T-Mobile in December, and he said 2030 is if we're lucky. And AT&T has said publicly 2030 to 2032 to get spectrum. And that was in one of the financial earnings discussions last year. Now, is there spectrum out there? Yeah, there is. Other people own it. Dish has got a bunch. You may have heard they have a few problems. So doing a deal to get Dish, you're not going to buy them for the subscribers. You're going to buy them for their spectrum. That was a sarcastic comment from Steven Yurgo, T-Mobile, talking about one of his competitors. Yeah. Just throw off my train of thought now. There is spectrum out there. You go buy Dish. And then there's other people who bought spectrum in the 3 gig band. There were investors who raised $1 billion or $2 billion and bought it and have been sitting on it waiting for the carriers to come. AT&T bought some last year from one of my friends like that. This is one of my friends who skis at Vail when I've been there for the day, except he's there for a week, and then halfway through his trip, he had a wedding to go to in Connecticut. So he just took his jet back to Connecticut for the wedding and turned around and went back to Vail on his jet. So he didn't ask me to go. But we've got to get through the next 5 years pretty much with what we've got. It's out there. There's deals to be done, but it's going to be expensive and it's going to take time. The good news is this administration is probably going to be extremely friendly to mergers and acquisitions. So the idea of a Dish deal getting blocked now because the amount of competition is reduced, probably not going to be a problem. I think that one will probably get through. And you can talk about lots of different combinations there as well. But that's a good question. There's two assumptions there. One is if Charlie's still in control, and two, if Charlie's still with us, he's getting on a bit, you know? So, yeah, the debt may just it may just become insurmountable, right? You can also do a deal where it looks like he's still a major shareholder, right? Maybe you buy Dish and then he gets a seat on your board. That may placate him, that type of thing. So, all right, let's talk about other stuff. The sun. This is a picture of the sun I took with the C-Star S50. See those black dots there? They are not marks on the lens. They're actually sunspots. So now please don't go outside and look at the sun and go, where are they? And God forbid, do not get a pair of binoculars or a telescope and look at the sun, because you'll literally will burn out your retina. You can buy filters that go on. You can actually get your phone and turn down the exposure on your phone and hold it up at the sun and see the sun. But it'll be a little dot like that. This is with the telescope. So the Earth is 8 light minutes from the sun, which means that the light that's out there right now left the sun 8 minutes ago. And actually, this is interesting. It's 1 AU. So it's astronomical unit. We measure, that's a standard measurement, is the Earth is 1 AU from the sun. Neptune is about 30 AU. So it's 30 times the distance. That's how big it is. Our little sun is about 4.6 billion years old, they think. And I hate to worry you, but in another 5 billion years or so, the hydrogen's going to run out. Basically, the sun is it's a fusion engine, right? So the hydrogen molecules glow together and produce energy, and that's the glow. So our sun will start to die in about 5 billion years. We're about halfway through. The sun is really kind of like a millennial, right? It's got another, it's a halfway, it's about, it's 25 or 30, right? After it runs out, it'll take actually another 2 to 3 billion years before it actually dies. It'll change color and get bigger, and a bunch of other stuff will happen. Yeah, so don't worry. Everybody you know and all of their ancestors will be long gone before this all happens. People actually worry about this stuff. This Musk guy worries about this. This is why we've got to get to Mars. Like he worries about this. But there is a great website. This is actually a photo of mine, but if you go to spaceweather.com, it tells you the weather on the sun, right? And these sunspots actually are like solar flares, and that's what disrupts communication satellites and all those types of things, causing electromagnetic interference. But it's a really good website, and it shows you where the northern lights are. You can see on the southern lights, and what's happening on the sun. And it's stuff you need to know, because don't worry about what's happening in Austin. This is important stuff. Ruben's like, yeah, rolling his eyes, like, yeah. You're going to remember this, Ruben. All right. I was going to mention this morning when Ruben was talking about, I thought I'd hold it. This was a discussion I had at the FCC just before the holiday. This is quite interesting. The network, when you think of the network, right? Most people don't think of the data center, those billions of dollars and all those GPUs, that cloud where Google sits, as being part of the network. Our thinking of the network starts with the fiber and goes through, in the wireless case, all the way through to the cell site. But the discussions that are happening now, the data center is part of the network. It is the one and the same, which makes sense if you think about it, because I told you that the core network, the core can sit up in the cloud, right? That cloud data center could be the same one that's running your Google search or holding all your, photos or whatever. So data center today is included in the network. And I think it's a really important distinction. So the infrastructure here is antenna, radio, tower, small cell, etc., base station, fiber, and data center. When we talk about the whole thing, when you talk about valuations, you've got to include that. And that's what I didn't know I did look at the agenda. I saw what you were talking about this morning, but the whole discussion that Ruben had on how you value data center is really how do you value part of the network, just as you would fiber, tower, radio, etc. Okay. The other interesting thing with data centers is everybody loves to jump up and down about how much money is going into data centers. And then they forget, well, you actually need a fiber connection to it. Otherwise, it doesn't work. It's like building a gas station in the middle of nowhere with no roads to it. Not going to do a lot of good. So all of this infrastructure depends on the data center. If you've got more data centers and you want to put more processing, you're going to need more towers and radios, antennas, because the end result has got to get to the people. And those people are sitting there, usually with a smartphone or a laptop or a smart TV on the end of a wireless connection of some type. So it's a important, character distinction is you've got to put the data center in that discussion as well. Okay. So let's talk about AI. It's getting just started. The stuff you've got today is pretty basic. I've been playing with a lot recently. ChatGPT, for example, what it can do today compared to 2 years ago when I was trying it, it's phenomenal. It is absolutely the amount of processing it can do and the amount of analysis it can do. It gives you reasons for something now, not just, Shakespeare wrote plays. That's what it would have said 2 years ago. Now it says Shakespeare wrote plays because he was inspired to do so by getting up at 3 a.m. because his wife was snoring or something like that, right? It's really, really detailed. For us in the telecom industry, AI today is answering chats in customer care and composing emails, right? So you go onto the website and you want some help, you click and it says, hi, I'm your AI here. What do you want? I want to talk to somebody about billing. Great, you want a new iPhone? No, I want to talk to somebody about billing. And that's what we do. We're not really doing network analysis and network management. Anything that is happening on the network analysis side is kind of a separate tool, and then an engineer is getting it and actioning it manually, okay? The next stage, and this is going to come fairly quickly, is where the AI does the analysis, it monitors the network, it makes recommendations on what should happen in the network, and then it changes it. Now, that last step may require an engineer to approve it, right? Let's roll out a software update. Probably want to approve that one and check it before you hit yes, right? But the point is that there's tools now going into the network to actually monitor the network performance and the traffic demand and make recommendations of what adjustments would make, what should happen. We've always done this manually, right? That's what network engineers do, and they're very smart. It'll happen faster. Eventually, it will happen more accurately. Probably not initially. We're going to have to teach this AI to do this, right? As you know, wireless networks are very complicated, right? You've got a lot of radios out there, a lot of sectors, a lot of towers. The final stage, and this is 10 years away, okay, is where the network is completely zero touch. And this is where the network is self-designing, tells you where to go build a tower, put a radio up. Self-administering, will adjust radio's power output, antenna tilt, etc., fully automated and proactive. It will know that Taylor Swift is going to play in Austin in 3 weeks' time, and that when one Taylor Swift concert is the equivalent bandwidth to an entire Super Bowl weekend. So when Taylor Swift played in Atlanta for 3 nights, that was 3 Super Bowl weekends over the course of 3 days, right? And you wonder where all this bandwidth is coming from, right? So that network will know she's going to play there and what the impact will be, and will make adjustments to the network ahead of time, ready for all those 13-year-olds and 14-year-olds and smiling people thinking, yeah, I like Taylor. There you go. I got in the car the other day. I'm like, who's this? And my wife said, oh, it's Taylor Swift. It's like, my wife's a Swiftie? What happened there? You're going to see this in 10 years within your careers. Some of you, some of, no. It's just people shaking their heads like, no, I'm not going to see this one. This is not, this is not 30 years away. This is not, this is probably actually, this one here will be 6G, definitely. This is probably 6G advanced, the fully, so call it 2035-ish type thing, but certainly before 2040. Will we still need people? Yeah. AIs can't put radios on towers. Haven't found one yet. Still going to have somebody to plug all this together, and somebody's going to have to design the AI that designs the network, right? So there is a lot of work involved in this, as well as a whole new generation of equipment. You couldn't climb up a tower and put a bloody radio up. How's the robot going to do it? All right, so this is what's interesting. I'm going to show you a chart in a minute. And it's a company, the company name is on the chart, I can't remember it. But the impact of various industries over the next 10 years, it looks at growth over different industries, manufacturing, healthcare, financial, etc. The top was information and communications. Us. That's what we do. We're in that category. We've got the most to gain from AI. And when I saw this chart, I asked the presenter, I was like, okay, is it because the telcos are going to use more AI for like chatbots and customer care? Or is it because AI needs connectivity to be successful, right? And the answer is yes, and yes, it's both. One, we're going to make as much use of it as healthcare is and financial services and all those types of things. But AI needs connectivity. You can't have it. You can't just put it in a data center. It doesn't work unless it's connected to the end user, right? And so we are to gain from building more network to match that data center capacity. Wireless infrastructure is that capacity. It is that infrastructure. Yes, it's fiber, but it's also the radios and the towers and all the things we need. Ruben mentioned this morning about, I was going to say, brain fade. Gosh, gone. What were you saying this morning? You said a lot of stuff. Yeah. It'll come back. See, I'm getting old. There's the chart right there. And you can see, if you look at these relative numbers here for the growth, education is interesting. Education has got the least to benefit from AI, which I thought was like, oh, kind of need that. My daughter's a teacher as well. So I guess somebody's going to program it. Public services, social services, yeah, touchy-feely stuff. Utilities is interesting because that's where all the power generation is. But you can see healthcare, construction all the way up, but information, communications is right at the top. That's what we need. So we've got a good way to go. I know what I was going to say. One of the other discussions that followed on from this is AI too big to fail, or is it a bubble, right? And Ruben and I were talking about this over lunch, is if you think of AI as being like this, yeah, it could be a bubble. We could get it wrong, but it's not. AI is like this. There's all these different things. We see ChatGPT and a few narrow things. There's a lot of work going on. And as somebody said, it really is not a bubble. It's very, very broad. Within that whole spectrum of things are projects that will fail. There are things that will not be successful that are frankly crazy. So we're going to have some failures, but it doesn't mean the whole thing is going to crash and burn. Some things are going to take off more than expected. Think back to the 4G days, Uber, Waze, all those type of things were enabled by a 4G network. The same thing will happen within the AI scope. There'll be things we don't even know about yet enabled by AI. And it's sitting on a data center, and it's sitting on a fiber network, and it's sitting on a radio network. Hostinger was the company that did this. They've got a whole bunch of statistics. It's kind of interesting. So one of the other things is countries investing in AI, the amount of relative investment, like Singapore per capita is off the charts. It is unbelievable. All right. So last couple of slides. Good timing. We have to make better use of what we've got. I've said this a couple of times. Our current networks and spectrum have got to support us for 5 years. By the current network, I mean that 5G advanced, it's not a new air interface, it's an upgrade, okay? The roads we've got are going to be the same roads. The cars on them are basically the same, bigger engine, bit more efficient, right? Maybe a better stereo, but it's going to be the same cars. We're going to have to do more fiber and data centers for the processing. You're going to get more out of a tower. You're going to put more equipment on that tower, more co-location. We're going to densify. Densification, more small cells, really stopped for COVID because we all left downtown. That's starting to reverse now, and we'll see more of that. But we've got to get these results / data / applications from the AI back to the user. How do we maximize this? How do your networks support the processing? What are the economics of this for AI? To be determined, right? How do you make money out of AI? If you're Google, I'm not doing Google searches and seeing ads. I'm just going in the AI on ChatGPT and asking it to do something for me. It gives me the answer. I just skipped all the ad revenue for Google. Right? That's a problem for them, and they're going to have to work that out. And so how the economics in all this work out? when you've got to build these massive data centers costing tens of billions of dollars. All right, I'm going to finish with this. You may recognize this. It's the moon. This photo I took this one, 9,000 miles from Earth, in case you're wondering. So here's what's interesting. I don't know if you know this, but when you see the moon, you always see the same side of the moon. You've heard of The Dark Side of the Moon? Great album. See, the old people laugh at that. The young people laugh. What's he talking about? There's this band called Pink Floyd. Okay. So originally the moon, when it was formed, it used to rotate as it went around the Earth. And over time, because we have tides, and the tides are caused by the moon, the gravitational, it actually changed the orbit of the moon and changed its rotation and fixed it. So as the moon rotates around the Earth, it goes like this, not like this. So you see the same face of the moon all the time. So the dark side of the moon, we've actually never seen from the Earth. You've got to fly around it and go and have a look. The moon's about 50 million years younger than the Earth, give or take. So 4 billion or so-ish. Lots of theories on how it was actually formed. And they don't really know. One idea is that this big comet came in as the Earth was forming and hit it, and a chunk flew off. Another one is that it was actually another planet that came in and got caught by the Earth's gravitation and stuff like that. All right. How many people have walked on the Earth, on the moon? On the Earth. How many people have walked on the moon? Anybody know? Who said that? 12? Anybody else? 0, cynic. Get a telescope, you can see the... Anyway, anybody else? No? How many countries have had people who've walked on the moon? 1. Yeah. It's really interesting. There are actually 12 people who've walked on the moon. They're all American men. You would think that the Soviets did it? No, never actually got there. Once Apollo missions had happened, they're like, oh, we're not bothering with that. They were all Apollo 11 through 17 up till 1972. A great series on Apple TV is For All Mankind. And it starts out with the Apollo 11 mission and what happens. And history is tweaked just a little bit. And it's what happens all the way through 2000 it's up to. Each series is a decade. And it is really quite fascinating from one little tweak of what happened on Apollo 11 to, it's well worth watching if you're a geek like me. The lunar landings, there's been manned, unmanned, and crashed. And USA, USSR, Soviet Union, and Russia, Israel, Japan, India, China, Luxembourg landed on the moon. They actually crashed on it. And then the European Space Agency, which is, all the rest of Europe. But why the heck did Luxembourg do that? And this image, actually, I got from Sky at Night magazine, and it shows you where the landing sites are. So 11 is here, and it's really easy to see. You can actually, obviously you can see the moon. If you look at a full moon, and you'll see the bright dot there, go up, and there's this bit that kind of sticks out, kind of looks like Europe, right? And then there's a bit there that sticks up, kind of looks like the UK, and that's right where they landed Apollo 11. And you can buy a telescope powerful enough to actually zoom in and see the lander still there for you cynics who don't believe anybody got there. The other sites are scattered around, and the ones, this one's pretty good. It's got the little car they rove around in. Don't know if you can still see that. But you can actually buy a telescope to do it if you're interested. So there you go. All right, that's it. Any questions?
Do you know about the 2 landers that are on the way there today that will be landing in 2 months?
Yes, and when I built my list, actually, I'd said, no, I'm going to do people who've crashed and landed. and unmanned, because there's Japan is on the way and China, I think. And they've got stuff they're doing. Yeah. China's actually been on the dark side as well. They went on the dark side and took stuff. And there are people who've actually gone there, had a lander, pick stuff up and return it back to Earth, which of course is what Apollo 11 did. We just sent Neil Armstrong to pick up a few rocks.